All right, so we're ready to start taking a look at examples for confidence intervals. And you'll notice that at the top of the examples page, I gave you already the formula for confidence intervals. You wrote it down in your notes, but it's good to just see it as many times as you possibly can. And the thing that was probably the most confusing for us was to take a look at this thing called Z star. So what we want to focus on next is actually calculating or finding Z star, because there's really no calculation to it. Okay, what we need to first look at is figure out what was our confidence level, because we know that Z star is going to be related to the confidence level. So for example number one, I see that I have a 98% confidence level. I'm going to write that as a decimal because I want to think about, all right, well, I'm going to assume my conditions are all satisfied and that I have a nice normal curve where 98% of all of my samples are captured here in the middle. Now I think about, okay, well, if that's making up 98% of the curve, how much is left over? There's 2% of the curve that's left over in these spaces over here, and that's divided up among these two evenly spaced pieces. Okay? Well, why do I even care about this? What I want to pay attention to is this guy down here, the cutoff, the bounds for my confidence interval are these marks where I divided up the area into those two small spaces on either side of the confidence interval. So what that tells me is that this is the number I want to look at inside my z-table. So grab your z-table and let's take a look. So here's my z-table. Now I'm going to go through this a little bit quickly because I know where these things are, but I trust that you are going to look through the z-table to find it yourself. So remember the cutoff area was 0.01. Now the numbers inside the table, all of these guys here, these are all my areas. So we were looking for inside the table the number that's closest to 0.01. And I start looking in this row right here where I can see the numbers 0.0107 and then 0.0102, but this is the one that I really like right here, 0.0099. That's the one that is closest to the area that I'm looking for, 0.01. So I look at what's the z that corresponds to that. Well, remember that the z is the stuff that's over here on the column going down on the leftmost side and then the row up at the top. Okay, so I look at the z that corresponds with that, 0.099, and it's negative 2.3, and then the column it's in is 0.03. And we can remember that we can write that out then as negative 2.33. So that means I can write out my z star as negative 2.33. Okay, so at this point I want to think, well, wait, should it be a negative number? Because I also have this z star over here on the right hand side. Well, remember that z star, if it's going to have both sides of a normal curve is symmetrical. So if this one over here on the left hand side is negative 2.33, what's going to be this one over here that's on the right hand side? It's going to be a positive 2.33. Okay, so what that means is z star really is a plus or minus value, and that should make sense because look at what we have over here. We had that plus or minus symbol. Okay, so I'm going to clean all that up. The plus or minus really comes from this z star, and normally when I write z star, I'm not even going to think about the signs plus or minus. I'm just going to write it as a number. Okay, so let's go ahead and take a look at example number 2. Example number 2 has a confidence level of 90%. So again, draw your normal curve. Think about the value that's in the middle of that normal curve, should be 0.90. And if I have 90% in the middle, how much do I have left for the outsides? I have 10%, and divide 10% in between those two spaces, and I have 5%. Now be really careful with your decimals here. That's 0.05, not 0.5, but 0.05. Okay, so go back to your table and look to see what number is closest inside the table to 0.05. So hopefully you're looking on the table, same side, and you notice these two numbers here, 0.0505 and 0.0495. Well, where's 0.05? It's actually right smack in between those two. So what's the z that corresponds with that? I have 1.6, and then the column that it's in is going to be either 0.04 or 0.05. So that means I actually have a few different options here. I can use the z of 1.64 or 1.65, or I find what's the number that's exactly in between those. And you'll see this a lot where it just splits the difference and we use the z-star of 1.645. So that's exactly what I want to use. Now, you're not going to be marked wrong if you were to use 1.64 or 1.65, but that's how you do it. So that means my z-star can be written out as 1.645. And there's my critical value. Okay? Go ahead and take a look at example number 3. Pause the video, take a look at your z-table, and figure it out. So now we should end up seeing, for this example number 3, a z-star of 1.28. Hopefully you got that one right. If you don't, take a look at the diagram and check with your neighbors, try and figure it out. Now, let's go ahead and move on to example number 4. Alright, so next let's actually build the confidence interval, and you guys, it's going to be way easier than it seems because we're going to break it apart in this first one. The next one we'll put it all together and you'll see how similar it was to everything we did in Chapter 7, Sampling Distributions, which you guys were all really, really good at. So, let's take a look. Tanya wants to estimate what proportion of her school's seniors plan to attend the prom. She interviews an SRS of 50 seniors. There are 750 of them in total, and finds that 36 plan to actually go to the prom. So the first thing that's always good for us to do is to actually look at what's the population and parameter. Well, our population is this thing that I circled. Population is big N, 750 seniors at her school. Right? That's no big deal. The parameter, what is it that we are trying to estimate? Right? We're trying to estimate the proportion of her school's seniors that plan to attend the prom. So we can write that out for our parameter. I'm going to label that as P, lowercase p, for the population proportion of her school's seniors that plan on attending prom. Okay, so the next thing we want to pay attention to is look at all of the conditions, right? We want to think about this in terms of that sampling distribution. So what's one condition we know we can check? We can check the 10% condition. Okay, so 10%, what was our sample size? Little n was 50. I'm going to write that off to the side. Big N was 750. Okay, so that means I can say, is little n less than or equal to 10% of big N? 50 was indeed less than 10% of 750. Done and done. So 10% condition is satisfied. Next condition we can check, we know we needed to check the LCC, right? Well, LCC, we had to do N times P hat, and we needed to see that that was indeed, let me clean that up, N times P hat was going to be greater than or equal to 10, and N times 1 minus P hat was going to be greater than or equal to 10. So when we look at that, we can plug in N was 50, but what was P hat? That I wasn't sure about yet. I haven't done that yet. So let's look at P hat. Well, we know we had a sample of 50 seniors, right? Of those 50 seniors, we said that 36 of those plan on attending prom. So if we plug in that to the calculator, we find that P hat is going to be written as a decimal 0.72. You can write it as a fraction, that's fine, but I think it's a lot easier to end up working with my calculator and verify these things to be true when I just use a decimal. So I check 50 times 0.72, and then if 72% said they were going to attend the prom, that means 28% said they must not be planning on attending prom. But 28% of 50 is still going to be greater than 10, so I can say that my LCC is checked. The last condition that we need to check is the random condition. So the random condition, that's our new one. All we need to say is that, hey, did we actually take a simple random sample or some kind of random sample? So we said, you know what, it says specifically in my prompt that I took a simple random sample of 50 seniors. So that condition is indeed satisfied. So now what this tells me is that I've got that normal distribution. I have a condition where I can check my spread of that normal distribution, and I should be relatively free of bias. So now I can go ahead and finally construct that 90% confidence interval. So let's go ahead and think about what that formula is. It's written up at the top of your notes, but let's write it out again. My formula for a confidence interval is p hat plus or minus z star times the square root p hat times 1 minus p hat all over n. Right? Same formula that's up at the top of the page. P hat, we know. We've got that. That's fine. Little n, we know what that is. The only thing we don't know is that z star, but we just worked on finding z star. And in fact, if you look up at your notes, we did find z star for a 90% confidence level already. At 90%, z star was 1.645. So let's go ahead and plug everything in to find our confidence interval. P hat was 0.72. Z star was 1.645. Take the square root of p hat, 0.72, times 1 minus p hat, 0.28, and then I divide that by my sample size of 50. This can be done in 2 steps in your calculator, right? What you need to do is add add 0.72 to this product, hit enter, get your result. That'll give you your upper bound. Then subtract. Doing the same calculation, the only thing you're changing is the subtraction symbol. That gives you your lower bound. So go ahead and write that out in your calculator, type it up, and get your result. So if you need more time, go and pause the video. But our answer here is 0.616 to 0.824. And I write this in interval notation, much like what we saw in 8.1. Put my lower bound in parentheses as well as my upper bound, separate them with a comma. Okay, so the next thing we can do is interpret that interval in context. And this is really simple. We just use that sentence starter template that we have from 8.1. Take a look at your notes if you need to, but here it is. Say, I am 90% confident, because that was my confidence level, that the interval from blank to blank, but what am I putting in for my blanks? I'm putting in my lower bound and my upper bound, from 0.616 to 0.824 captures the parameter. But again, what's my parameter? We already wrote out what the parameter was. It was up at the first part of this prompt. It was the true proportion of seniors at Tanya's high school planning to go to prom. Done and done. True proportion to emphasize that this is for the entire population. So that's interpreting a confidence interval. Okay? Not that big of a deal. Even with this one, we broke it apart and we wrote a little bit more than what we needed to. So I'm going to try and, with the next example, make it even more efficient so you have less to write and less to think about. So let's take a look at it. Alright, so this is one of my all-time favorite examples because I'm just sure that some really nerdy author of our textbook is just like me and would totally do this with their kid, and in fact probably did do this with their kid. So, great example, let's read it. In her first grade social studies class, Jordan learned that 70% of the Earth's surface is covered by water. She wondered if this was really true, and she asked her dad for help. To investigate it, he tossed an inflatable and geographically accurate globe to her 50 times, being careful to spin the globe each time. When she caught it, he recorded where her right index finger was pointing. And in 50 tosses, her finger was pointing to water 33 times. We want to construct and interpret a 95% confidence interval for the proportion of Earth's surface that is covered by water. Based on this confidence interval, do you doubt the claim that Jordan learned at school? So, what's the claim? Ultimately, the claim is the thing we're trying to test. It's the thing that we are a suspect of. And that is whether or not the real proportion of the Earth's surface is covered in water is 70% or 0.70. Now, let's write down the other things that we know. Well, we took a sample, right? What was this sample? The sample was actually just tossing this globe at his kid. So that was how many times we tossed the globe, and that was 50. Well, how many times could he have thrown the globe at her? That's our population size. And our population size here is an extremely large number. It's infinite, really. He could be still tossing that globe at her to this day. I only needed to be large enough to satisfy the 10% condition, so I say the n must be much, much bigger than 500. The next thing I can look at is that in those 50 tosses, her finger is pointing to water 33 times. So that tells me that if it's totally random, we're just like throwing darts essentially at the globe, and will it land in water? That's going to give me my sample proportion. And my sample proportion could be thought of then as 33 out of 50. Right? Which means we essentially have a 66% chance that we pick a random spot on the globe that is covered by water. So now we have some evidence, right? We say that there's a 66% chance that a random spot is covered by water, but the claim was that 70% chance of picking a random spot on the earth and it's covered by water. Okay, so let's see, is it plausible that 70% is true despite our evidence? So let's look at our confidence level. The confidence level was 95%. Okay, why do we care about that right now? Because we want to find Z star. So we think about Z star at 95%. Go ahead and draw out your normal curve. Here's your 0.95. There's 5% divided up between each of those two areas. If we take 5% and divide it into 2, we get 0.025. Okay, so take a second, look at your Z table, and find your Z star. Go ahead and pause the video and then resume once you've found it. This gives me a Z star of 1.96. Okay? So I've written down everything I know. The next thing I want to look at is, well, what are my conditions that I need to check? So let's go ahead and check some conditions. Okay, conditions to check. First one we can do is, hey, did we have our random conditions satisfied? Well, we can think about this tossing of the globe as a random chance process. So we can think about them as random tosses, and it's like a random selection of all possible tosses. So we could say that these are random tosses of a globe. And that condition is then satisfied. The next one we can look at would be the LCC. When in that case, and we're getting really good at this now, right? We don't need to write down n times p hat all the time, so let's try and make this a little bit quicker. We'll say that it's 50 times my proportion from my sample times 0.66. Well, I know that 66% of 50 is much bigger than 10. And if 66% of the time her finger landed on water, then that means that 34% of the time it didn't, right? So that means I'd multiply those two and I see if it's bigger than 10. Well, I do know that 34% is bigger than 10, so that means I have satisfied my normal condition. Check. Last condition to check is the 10% condition. 10% condition should be pretty easy because we defined it in that way, saying that 50 is going to be less than 10% of my population because we know we can throw this ball many, many more than 500 times. And that means that the 10% condition is going to be satisfied. Okay? So the next thing is to actually plug into our formula. Now, for the formula, I do want to actually write it out. So my confidence interval formula, because I'm still learning it, I want to write it out. P hat plus or minus Z star times the square root of P hat times 1 minus P hat all over n. Okay? And make sure you're very clear with your square root symbol that that is extending over the entire fraction. Okay? And let's go ahead and plug in. For P hat, that was the 0.66. My Z star, we found that to be 1.96. And then we have the square root of my p hat, 0.66, times 1 minus p hat, that was the 0.34. Divide that by 50. Punch this into your calculator. Pause the video to punch it in, and then double check my work. And spoiler alert, here's the confidence interval. Pause it if you're still watching, but it is 0.529 as my lower bound to 0.791 as my upper bound. Okay, so there's my confidence interval. Unfortunately, I'm not quite done, right? We first of all want to say I'm constructing and I'm interpreting that confidence interval. So we can write out that statement by saying I am 95% confident that the interval from 0.529 to 0.791 captures the true proportion of the Earth's surface covered by water. I still have one more question to answer ultimately too, and that question is, based on my confidence interval, do you doubt the claim that Jordan learned at school? Well, let's go back to the claim. The claim was that 70% of the Earth's surface is covered by water. And we want to know, is that plausible or is it implausible? Well, remember, our confidence interval is an interval of plausible values. So is that 70% inside our interval of plausible values? And it turns out that it is. So we can say, therefore, the claim made by Jordan School is plausible. 0.70 is in the interval. Done and done. All right, guys, thanks for watching. You will be able to complete all homework problems except for numbers 45 and 46. We will continue with those next week. I will see you later.